Here we go. Determine the number of terms n in each arithmetic series. Sum equals n over 2 first term plus last term. Sum in this problem is 1365. N is what we're solving for. First term would be what? How do I get the first term in this one? Plug in 1. So 3 times 1 minus 1 is 2 plus. And then how do I get the last term? Plug in n. 3 times n minus 1. You might recognize this as the type where you have to plug the equation in for t of n. And luckily, they gave you the equation. You just have to make sure to use n because you have to use the same letter. Okay. I'm going to times by 2 on both sides. Okay, these cancel. And then I'm going to combine this and this. 2 minus 1 is 1. So 1 plus 3n. Distribute. Okay, now when I get to here, I'm going to write these things in order. So the 3n squared is going to come at the beginning, then the n, then minus 2730. I know I'm setting myself up for quad formula, so I want to go A, B, C here. A equals 3, B equals 1, C equals negative 2730. Now this actually is factorable. You can factor that. I just wouldn't even try because of the 2730. But it's totally possible. This should be n equals, okay. N equals negative b plus or minus square root b squared minus 4ac all over 2a. A lot of you guys that have been doing these problems, I've been really happy because if you come over and ask me a question, it's because this does not come out evenly, and you know that it should come out evenly, which is good. So if it doesn't come out evenly, we did something wrong. 1 squared minus 4 times 3 times negative 2730. And then square root 181. So I have n equals negative 1 plus or minus 181 over 6. And remember with quad formula, in a problem with a series, you only worry about the positive one. The negative one's not possible for what we're doing. So negative 1 plus 181 over 6, which should be 180 over 6, which is 30. There's a problem extremely similar to this one on your quiz. Very, very similar. So I'm glad we got to do it together. Okay. Now we have a geometric one. It has a different formula. Sum equals first term times r to the n minus first term over r minus 1. Sum is negative 182. Okay, now this is where you might get stuck if you're going to get stuck. First term is 1. You can get that by plugging a 1 into the formula here, or You can get it by knowing that there's a 1 in front of the parentheses because there's nothing there, so that has to be a 1. So 1 times negative 3 to the n minus 1 over negative 3 minus 1. Any questions about my plugging it? You guys okay with my plugging in? Okay, now I'm going to multiply both sides by negative 4 to cancel out the denominator. So I don't like this problem. Does anybody see why I don't like this problem? No, I mean, I don't mind the logging part. I'm looking for a detail. By the way, I'm just going to divide by 1, even though I know that's silly. Okay, now that I'm down here, can you see why I don't like this problem? You can't log negative numbers. It'll just give you an error on the calculator. So we're just gonna ignore the negative. I hate that a lot. Don't like it. I just wrote your chapter 10 test, and there's a problem like this, but it does not have a negative there. So don't worry about that, please. Ah, now this is not on your quiz. What this is. Okay, we are not done with the packet for today. There's a resource page we're going to use. It says 10-179. If you could find that page, please. Should be right after Pascal's triangle. It looks like this. Okay. First, set this up though. So interestingly enough, the first two problems of today's classwork are a video that you're going to watch. It's about compounding interest, the bank stuff, and figuring out what is E. When you write that, what is E? E is a number like pi. It's very similar to pi, actually. It's an irrational number that never ends and never repeats. But it's a very special one. You probably maybe noticed the buttons for it on the calculator that you haven't used yet. If you look over by the log button down here, buttons that you haven't used. This is the log button, and the log base 10, its inverse is 10 to the x. And this is what we're learning today. This is ln log natural log, and its inverse is e to the x. So we need to figure out what number e is. What is e? You didn't even know that e was a number, did you? Probably not. You did know? Maybe. You might have used it in science, actually. It's kind of a sciencey concept. But anyway, so here is this. So if you guys could just relax and watch this, please, for the next 9 minutes and 30 seconds.
The two most common logarithms used are log to the base 10 and log to the base e. Why are they the most commonly used logarithms? How do we really understand them? Log to the base 10 is kind of intuitive. It's easy to talk in multiples of 10. 10, 100, 1000, and so on. Log to the base 10 gives us an easier scale to work with. Log 10 to the base 10 is 1. Log 100 to the base 10 is 2. 1000 to the base 10 is 3.
You guys
And
see
we can see that the multiples of 10 can be managed with a scale of natural numbers. But log to the base e is what I'm deeply interested in. It's called the natural log, and it's also written as ln. Yes, log to the base e is also written as ln. So log 20 to the base e can be written as ln of 20, the natural log of 20. What is this e? Some call it a magical number. Some call it an irrational constant. Some call it a Euler's number. But the harsh truth is this: very few people actually understand what E is. To get to E, we first need to understand growth. Let's say a particular thing doubles every time period. On this timeline, this is today, and every unit is one time period. Assume you have $1 with you. At the end of the first time period, this dollar doubles and you have $2. At the end of the second period, $2 double to become $4. And at the end of the third period, we have $8. How do we look at this growth? First, we see that the numbers at the end of the time periods are powers of 2. It's in the form 2 to the power x, where x is a non-negative integer. 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. This was one way in which we looked at double growth. Another way to look at it is that there is 100% growth every time period. 1 plus 100% of 1 gives us 2. $1 was increased by 100% to get 2. In the second time period, $2 grew to $4. 2 plus 100% of 2 gives us 4, and so on. So doubling the value is the same as a 100% increase. So 2 raised to x can also be written as 1 plus 100% raised to x. It's like you're getting a 100% return on your investment. But hold on, we are making an assumption here. We are assuming that growth happens in a discontinuous fashion. We are seeing growth in steps here. What about the time in between two time periods? We are seeing no growth in between. No growth, and it suddenly doubles. Again, no growth, and suddenly doubles. But hey, that's not how nature functions. Everything or every kind of growth happens gradually. If your height today is 4 feet, you suddenly won't be 5 feet a year later. Your height gradually grows.
This is
When
not
we
studying
started,
time.
we used to get around 30 views a
Not
day.
studying time.
And after a year, we started getting around 4,000 views a day. It doesn't mean our view count just jumped one fine day. It gradually increased. So growth in nature is never really discrete or discontinuous. Let's see how it really works. We take the example of a dollar growing over 1 year at a 100% growth rate. First, we look at the annual growth. Based on what we saw, at time zero, we would have $1. And at the end of the year, we will have $2. This doesn't seem right because all the interest cannot appear on the last day. To make it slightly better, let's divide the year into two equal parts, 6 months and 6 months. Splitting that 100%, the growth would be 50% in the first year and 50% in the second. It would look like this. Our initial dollar earned 50% interest in the first half to give 50 cents more. Now what happens in the second half? $1.50 remains as is. The growth is 50%. So 50% of $1 will be 50 cents. And this time, the 50 cents also earned a 50% interest. That will be 25 cents. This 1.5 is the sum of our original dollar and the 50.
Okay, I have to pause this here because she's assuming that you know stuff that you probably don't know about money because you're sweet children who just have plastic cards that you use and don't have any actual money on you anymore. But when I say compounding, there's a very important word there that you probably don't know called compounding. You know what interest is, probably. Making money on something like an investment. But compounding is the word you probably don't know. Okay, so we're gonna slow this down. You have $1. Okay. 6 months in, you have your original dollar, and the dollar made 50 cents interest. Is that okay? So you might actually not know this. That's how banks make money. Banks make money by taking the money that you give them, like you put your money in a savings account, right? They take your money and they invest it. They give you part of it, but they keep the rest. That's how banks survive. Banks are not just like nice places to guard your money for you. They actually are businesses that make a profit. Their profit comes off of borrowing your money, investing it. They give you a little bit back to make you feel better, but they keep most of it for themselves. Just true fact. So the bank took your dollar, they guaranteed your original dollar, they invested your dollar and made some money and they gave you 50 cents of it. Okay, are you good with that? Okay, this is the part where the compounding comes in. Compounding means that this 50 cents dropped into your bank account and now you don't have $1, you have $1.50. And so this is your new balance, which is $1.50. Compounding is when that money that the bank made drops into your piggy bank. That's yours now. That's what compounding is. Okay. At a year, you have the $1.50 from the 6 month mark. The dollar they invested and gave you 50 cents. And then the 50 cents they invested and gave you 25 cents. And then at the end of that, you guys see the 25 cents and the 50 cents? That's going to drop into the $1.50 and that will be compounding. So compounding means the money's yours now, which is great. We like money. I like money. I like to buy stupid stuff, squishmallows and things.
Cents
Candy.
we made here. So at the end of the first year, we have our original dollar, then we have the dollar that made our original dollar made, and we also have the 25 cents that these 50 cents made. A total of $2.25. This is better than doubling. If we want to understand this using a formula, it would be 1 plus 100% over 2, the whole squared. We had half the growth rate over 2 time periods. This is also referred to as semi-annual growth. Let's push ourselves further. What if we had 4 equal time periods in a year? We have divided 1 year into 4 quarters. This is how it would look. Looks messy, but it's actually very simple if you've understood the concept. It's 25% growth every quarter. The formula would change to 1 plus 100% over 4, the whole raised to 4. We would approximately get $2.441 at the end of the first year. I suggest you pause the video and understand the quarterly growth diagram really well.
Already did that, but I figured the
100%
semi-annual would be easier.
is nothing but 1. If 2 time periods, then we have 2 here. If 4 time periods, then 4 here. So the formula for n time periods would be 1 plus 1 over n, the whole raised to n. Clearly, more the number of time periods, higher will be the returns. This will give us the dollar value at the end. I probably know what your greedy brain is thinking. Is it possible to get unlimited money? Let's make a table now. Number of time periods and the dollar value in the end. If it's just 1 time period, the dollar value is 2. If 2 time periods, then $2.25. If 4 time periods, then $2.44. If I divide the year into 12 equal time periods, my return will be higher than this. If I divide it into 365 equal time periods, it will be even higher. This tells us that $1 at the start of the year will become these many dollars at the end of 1 year if the number of time periods is 365. So if we increase this number significantly, that is, if we increase the number of time periods significantly, will this number also increase significantly? Okay, here are a few more calculations. The number of time periods here is 1 million. Notice that the returns improve, yes, but they converge around a value which approximately equals 2.718. And that is your beloved E. We can't get infinite money after all. What would be a layman-friendly explanation for E then? It is the maximum possible result after continuously compounding a 100% growth over one time period. Yes, that's E. Don't forget, we had assumed a 100% growth here. And that's what E is. It's the maximum we get after a 100% continuous compounding growth over one time period. Notice what compounding does. The first result is 100% without compounding. $1 would become $2. But after continuous compounding, $1 will become $2.718 approximately. That would be a growth rate of 171.8%. That's like the maximum growth we can have. So E is approximately 2.718. It's an irrational number, which means the digits after the decimal point do not repeat and go on forever. Just one last question. What if the growth rate and the time period change? Will E still help us? Absolutely. There's no problem at all. In general, the growth after continuous compounding is given to us as e to the power r times t, where r is the rate and t is the number of time periods. So if we have a 200% growth for 5 years, then it would be defined as e to the power 2 times 5. We squared e to include 200% growth, and we raised it to 5 as there are 5 time periods. It'll give us e to the power 10. E is nothing but the maximum possible result after continuously compounding a 100% growth over one time period.
Fascinating. Okay. I wish the banks worked like that. They don't really. This is a lot theoretical stuff. Okay, what we're gonna do is take the two formulas that she gave us and put them in these spots. But we're going to leave some room, like put them in the middle so we can define the letters. So we're gonna say A equals P 1 plus R over N to the NT. So start with that. And she only had this part in the video, but she was starting with $1. I don't want to always start with $1. So that's why we have this. And then this gives us the opportunity to do more than 1 year. Okay, so let's define what these things are. A is your new amount. P is called the principal. That is a banking word for your initial amount. Again, in the video, she didn't have P. That's because she was starting with $1. So her P was 1. This right here is a 1. Okay. R is the rate as a decimal. In her formula, she had 100% there. So that would be a 1 for her. But we're never going to have 100% growth in the real world with banks. Bless their hearts. They're not going to give us that much money. Okay, N is the number of times compounded per year. And T is time in years. I have to be honest and tell you, these problems are extremely easy, which is good because, you know, it's April and stuff. We want to have some stuff be easy. Really, we're just going to plug things into these mostly and just solve for the letter that's missing. Why on earth is this happening now? Well, it's happening now because sometimes the time is the variable and you need to be able to log. So these are log problems sometimes. Most of the time, we're just going to plug in and use the calculator. Okay, now compounding continuously, that's the one where she was talking about E, and I like to call it PERT. A equals PE to the RT. E is a number, everybody. That is not a variable here. That's a number. 2.718, blah, 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 blah. Okay, but let's define these other letters. This is the new amount again. This is the principal. Just the initial amount. E is not a variable. I'm not going to define it with an arrow and say what it is. It's just E. On the calculator, if you want to find E, it's right above the natural log, which is right next to the 4. So if you go second natural log, it'll give you E. It's going to want an exponent. If you want just plain E, do E to the first. There you go. There's your 2.718, blah, 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 like she was saying. R is rate as a decimal. And T is time in years. Okay. Okay, you're gonna want a calculator. You don't have one to figure out what you get after you plug in these formulas. Okay, so we're gonna start with this first one. Quarterly. When it says quarterly, you know you're in this section because this is compounding time periods. Time periods, quarterly is a time period. It's once every 3 months. So A equals. Okay, what is the principal? Principal is the initial amount. What number up here is the principal? 10,000. Okay, now this right here is a 1 plus R over N. R is a decimal. So what's 3% as a decimal? 0.03. Okay, now if you said 1.03, it's because you're thinking about math 1, where you do this, you don't consider compounding, and the multiplier would be 1.03, but we have to consider the compounding in math 3 here. So how many times per year is it going to be compounded if it's quarterly? 4 quarters. 4 quarters. Quarters are 4. Okay, and then that 4 is the same as the N here. So these are both the same. And then it says for 10 years. Okay, so all that's left to do is calculator. $10,000. 1 plus 0.03 over 4 to the 4 times 10. Okay. Now don't look silly like you've never held a dollar in your life. Make sure that you round to the nearest penny. So this would be 49 cents. Okay, so that's what you would get at the end of 10 years if it was compounding quarterly. Now we're going to do continuously. Because it says continuously, that means you use this formula, which is PERT, PE to the RT. Principal is still the same, 10,000. E is a number, that's not a variable. It's 2.718, blah, blah. R is 0.03. T is 10. 10,000. And then this might be your first time using the E to the button, which is right above the natural log. So you have to do second natural log. 0.03 times 10. As you can see, compounding continuously would get you more money, but there is no bank out there that compounds continuously. So that's just a theoretical number. It's the maximum possible, but you'll never get that. Bless your hearts. Neither will I. I don't even know if you can find a good interest rate anymore these days. But anyway, okay. Done with the notebook. I love these problems, by the way. Just find the stuff, plug it in, calculator, move on with your day. All right, now, the last problem for the classwork is this page. And the reason is because as much as I like CPM sometimes, CPM believes that all I have to do is explain to you what natural log is, and that you'll be able to apply everything that you know about regular logs, and that you don't need any practice on natural log or E. So Ms. Rice and I created this because CPM didn't have anything. Okay, the truth is you know a lot about this already, but it's your first time seeing this symbol. So what we're gonna do is I'm gonna do the odds, and then I want you guys to work on the evens. And then at 9:30 is where I'm gonna stop you wherever you are to set up for the quiz. Okay, so this is just a log problem. The first thing you do is look at the operation. Operation is subtraction, which means you have division. You guys remember? Subtraction is division. Okay, so natural log 4 over 5x equals natural log of 2. You know how to do that. It just looks weird because it's natural logs. And it's been a minute for sure. When's the last time you did some log problems? If you did the CAS packet, they were in there. The whole point of them was to remind you how to do this. Okay, anyway, natural logs on both sides, they cancel. 4 over 5x equals 2. Multiply both sides by 5x. 4 equals 10x. Divide by 10. Divide by 10. 0.4 equals x. Just like the other log problems, we round to the nearest 10,000th, which is 4 decimals, but this one came out evenly. Okay, how do you feel about that first one? You okay? I'm not going to do this one with you, but this is plus, which would mean what? Times. And you're going to have to distribute that 7, just say. Okay, move down to number 3. Subtraction is division. Natural log 9 over x equals 3. Okay, this is different. I don't have natural logs on both sides. Do you guys remember what we used to do with a log when you didn't have it on both sides? Guide and circle. Okay, we're going to do guide and circle with this. We're going to take ln and we're going to change it to log base e. ln is just shorthand for log base e. These are the same thing. And now we're going to do guide and circle. E to the third equals 9 over x. Okay, now I'm lazy. I'm a really lazy human. I'm going to keep this e to the third, just e to the third until the end, and then I'll make the decimal. So times x on both sides. Nine divided by e to the third. 0.4481. Okay, do you think CPM was right in just skipping over all this? I feel like you know most of it, but like this little business here, probably not. And then you probably feel weird about having this, like that looks weird to you still probably. Okay, number 5. Number 5 is a cat in a tree problem. Cat in a tree. Okay, so what do we do first when we have operations on the base and exponent? Yeah, perfect. So add 1. Are you with me so far? Okay, now what will we do here? There's a cat stuck in the tree, so we what? Hit it with a log on both sides. Okay, very specifically though, you need to hit it with a natural log. Why do you need to hit it with the natural log? Because there's an E in the problem. Since there's an E in the problem, you hit it with natural log. The n plus 2 still comes in front. Natural log of E equals natural log of 10. So you're still logging both sides. You're still moving the exponent in front. It's just that you're picking natural log. Why do we pick natural log? Because natural log and E are inverses. They cancel. Okay, this might be your first time ever hitting the natural log button on your calculator. Natural log of 10 minus 2, 0.3026. Okay, last one. What do I do first? Add 8.2. On these problems, we don't worry about the fact that we have weird decimals. It's just going to happen. Okay, step 1, add 8.2. What's step 2? I can't log with that -8 in the front. What would I do with it? No, divide. You have to have this alone before you log. Okay, now I'm going to log. What's going to happen to the v minus 3? It's going to go in front. I like to put it in parentheses. And what log should I choose for this problem? Natural log, which you're going to write ln. I know it's weird, log natural, but I think they did that because they wanted the log buttons to be next to each other and both have an L in the front. I can't think of any other reason. Natural log and E cancel. That was the whole point. Okay, I want you guys to work on the evens. I am going to hunt for the answers for those evens and put them up there so you can make sure that you can check yourself. But go ahead and work on the 4 evens while I hunt down the answers. You guys can talk about them, please. Yeah. Hey, you guys. Those are the answers for the 4 evens, so you can check yourself. I have the key over here if anyone needs it.